Good morning. I myself Ajay Kumar, working in the Department of CSA as an assistant professor. And today I would like to explain you the topics time and space complexity and asymptotic notation in ADS and algorithm analysis. So what is time complexity? So the time complexity is the measure of the amount of time an algorithm takes to execute. So before writing an algorithm, we have to see what time it will take to execute, right? So, and one more thing. So why we are using this time complexity means, so it will compare the efficiency of different algorithms. So for example, if you are taking linear search and binary search technique, right? So linear search will take more time to execute, whereas binary search will take less time to execute. Okay, there will be less comparisons in binary search, whereas in linear search there will be more comparisons. So that's why we are using the concept of time complexity. Okay, and predicts how they perform for large input sizes. See, if you take, for example, 3 numbers to calculate, it will take less time. So if you take 100 numbers to calculate, it will take more time to execute the algorithm, right? Next, so one more thing you have to remember, the execution time. So it's depending upon the size of the input, right? If you are giving the input values a small one value, so it take less time to execute. So three values, less time to execute. Or if you take 10 values, so it may take a little bit more time when compared to the previous one. So as well as it will depend upon the value of n. So as n increases, the running time may increases. So the running time increases at different rates. If you take, for example, n value as 10. So if you implement that in for loop, so it has to run for 10 times. So if you take, for example, 2 for loops in a program, so it will execute 10 into 10, 100 times. So the execution time depends upon the value of n. As the n value increases, the execution time also increases. So now we will see the different factors why we have to use the time complexity. So as we discussed before, the time complexity is used to compare the algorithms. So for example, linear search and binary search, and to predict the performance. So how efficiently the algorithm will works. And the next is to choose efficient solutions. See, for example, for a problem, there may be number of solutions. So out of that, we will choose a better solution. And to improve the algorithm design. So if there is any problem in the algorithm design, so we may rectify after the time complexity execution, right? To study scalability. So what is meant by the scalability? Scalability means if you are giving more input to the program. So for example, if you give 10 values first, and then input values may increase to 20, and then may increase to 30. So how efficiently the algorithm is working. So to improve the scalability. So even though we are giving the input values more, so the algorithm has to work efficiently. So that's why we are using the concept called time complexity, right? And I'm moving to the next slide. So on what factors does our time complexity depends? So it depends upon number of loops. See, for example, in an array program, linear array program, we are using only one for loop. That is, for I is equal to 0, for I is equal to 0, I less than n, I plus plus. Right? So this loop will work only for n times. Right? If you are using one more for loop, that is for j is equal to 0, for j is equal to 0, j less than n, j plus plus. So here it will work for one more n times, that is n into n, that is n square times. So for I is equal to 0, I less than n, I plus plus, it is n times. And next for j is equal to 0, j less than n, j plus plus, it will take one more n time, that is n into n, n square times the loops will execute. And nested loops. So if you are using nested loops, so to print a pattern program, so we are using different nested loops in the program, so it will take more time to execute. And then recursive calls. So if you are using a recursion concept, so what is meant by recursion? It is a function calling by itself. So the function has to call by itself number of times. So once if there is a terminating condition in recursion, it will come out. Next, input size. So as we discussed in the previous slide, if the input size is small, the time taken to execute the algorithm also it will take less time. So if it is more input size is more, so 10, 20 or 30 or 40, so it will take more time to execute, right? Algorithm design. So how you are writing the program. Okay, so as we know, we can write a program in different ways. See, for example, swapping of 2 numbers. So we can use 2 different logics. So by using a temporary variable and without using a temporary variable. So like that, if the algorithm design differently, so that is also one of the factor that is affecting the time complexity. Okay, and this will be measured by using the asymptotic analysis. So asymptotic analysis is a method of evaluating the performance of an algorithm. So basically, why you are using this is to implement the performance of an algorithm, right? So and it's depending upon the running time. So, and well as the input size. So this asymptotic analysis mainly used to find the performance of an algorithm, and we have to analyze. So how much time it will take to execute. Okay. Right now I will show you what are the different things in asymptotic analysis. The first one is the big O notation. So big O notation. So we have to represent by using this. It is a worst case. Worst case means the maximum time required to execute an algorithm. Okay, so that means it is the upper bound of an algorithm. Okay, so see here, if you take a function f of n is equal to O of g of n. Okay, so what is this order of g of n? So g of n means it is the maximum time required to execute an algorithm. So if you take, for example, linear search, so I'm writing here 1, 2, 3, 4, and 5. Okay, so if I want to search an element whether 5 is in the list or not, right? So what I have to do, you have to do all the 5 comparisons, right? 5 so you have to first do the compare the search element with the remaining one. First one, 1 is equal to 5. Okay, is it true? False. So next, 2 is equal to 5. False. 3 is equal to 5. False. 4 is equal to 5. False. So 5 is equal to 5. True. That means you have to do here 5 comparisons. Okay, that is the maximum time taken to execute an algorithm. So it is represented by using f of n is equal to order of g of n, and t of n is less than or equal to c into f of n. That means this function will not reach the maximum allotment for f of n. Okay, t of n is less than or equal to c into f of n. And next, big omega notation. So it is a minimum time required by an algorithm. Okay, minimum time required to taken for by an algorithm. So if you take the same example, that is linear search, 1, 2, 3, 4, and 5. Okay, so what is our concept? In linear search, we have to search whether the element is in the list or not, right? Now I want to search whether 1 is in the list or not. See, where is the 1? It is in the first position itself. Okay, so we will do the comparison like this. 1 is equal to 1, right? The search element is the first position itself. Then it will take less time to execute the algorithm. So this is the concept of big omega notation, which will represent the best case. So the minimum time required by an algorithm. So and as well as it will return the lower bound. So it is represented by omega notation, right? And see here, p of n is greater than or equal to c into f of n. That means this time complexity will be greater than the function. And next, big theta notation. So big theta notation, it will represent the average case of an algorithm. So that means it will take both the upper bound as well as the lower bound. So it is represented by the big theta notation, theta of f of n. Okay, so mathematical notation is p of n is equal to O of f of n. See, for example, what is the worst case? Okay, if I take for example, I have to search the element 6 in the list. Okay, so then what we have to do? We have to do all the comparisons. Okay, at search element with this element. So 1 is equal to 6, 2 is equal to 6, 3 is equal to 6, 4 is equal to 6, and 5 is equal to 6. So 6 is not in the list. So we have to do all the comparisons. So if the element is in the list, we have to do the comparisons. So if the element is not in the list also, we have to do all these comparisons. So that is represented by using a big theta notation. So which compares both upper bound as well as the lower bound. Now we will see some examples. So this is a linear search. Okay, so we are using one for loop. For int I is equal to 0, I less than n, I plus plus. If a of I is equal to I, return a. So if the element to be searched is in the first position itself, or if we found the element, so then we are going to return I. So it is represented by using time complexity, order of n. And next, if a of 0 is equal to key, that means if the element is in the first position itself, so it is called as a best case. So that's why we are going to represent by using omega of 1. Okay, so for int I is equal to 0, I less than n, I plus plus, print a percentage d a of n. So what here we are using the value of n, and we are going to represent all the values which are in the array. So we are going to represent here time complexity is theta of n. That means we will do all the n comparisons here. It is going to print all the n values. That is the time complexity. So there are 3 examples. Okay, see the comparison here. The best case of linear search, it is omega of 1, and for binary search, omega of 1. So what in the linear search, if the element to search is in the first position itself, then our searching is over. Similarly here, if the element to search is in the mid position itself, then we are going to do omega of 1 comparisons, right? And next, average case. Average case means if the element is in the list itself, or if the element is the last position itself, so you have to do this all n comparisons. So that is theta of n. So here omega of log n comparisons, right? That's the worst case, O of n and O of log n. And what is called as a space complexity, space. So space complexity means the amount of space required by an algorithm, its execution. Okay, so we are writing number of lines in a program, right? See, if you take a small program, so a small C program, that is addition of 2 numbers, as include See here we are going to add two numbers, right? And I have taken three variables int a comma b comma c, and I have read the variables and use the statement c is equal to a plus b and store the value in c. So print a percentage d. So this is a small C program. So in this we will count only the variable space. Okay, how many variables are used in the program? We are using three variables. So and each variable will occupy how many bytes? 2 bytes. So if you take for example 4 bytes, it will occupy 3 into 4, 12 bytes. So if you take for example a 32-bit machine, it will take 2 bytes of memory. So totally it will occupy how many bytes of memory? It will occupy 6 bytes of memory. Okay, so there may be number of statements in our program. So majority we will count what is the space occupied by the variables. See, so it includes memory for input data, memory for variables and constants, memory for data structures created by the algorithm, memory used by function calls or recursion, stack. Okay, so here what is meant by constant space complexity? So space complexity is classified on how memory grows with the input size n. So if you are using a single line in the program, that is c is equal to a plus b. So if you change the values of a and b also, it will take the same time to execute. So that's why the constant space complexity is O of 1. Okay, so if you are writing a for loop, it's different. So but using if a single statement, it will take O of 1. So that's why we are calling this complexity as constant space complexity. Okay, constant space complexity. If you change the values of n also, it will take the same time to execute. Why? Because we are using the single line here. This c is equal to a plus b. Next, so logarithmic space, it is order of log n. So here in the binary search concept, what will happen if the search element is in the mid position itself? So the comparison will be completed within a less time. So but if the search element is not in the mid position, so what we have to do? So we have to divide the list into two subparts. So left sublist, or you can call it as left subarray, or you can call it as right subarray. So here if it is a mid element. Okay, so if it is less than, if the search element is in the less than the mid element, so what we have to do? We have to divide the list into two parts. That is the left sublist as well as the right sublist. So divide into two subparts. Okay, so if it is greater than the mid element, so do divide go for right comparison. So left sublist, right sublist. Okay, so now again the same process. So divide this calculate the mid element. So mid is equal to low plus high by 2. And again search where the element is in the mid position itself. So if it is in the mid position, okay, otherwise divide again the list into two sublists. So that's why the logarithm is calculated as O of log n. Okay, the same process will be repeated until the element is found. So until until the list is divided into a single element, so our process will be continued. Okay, and next is the linear space complexity. See here we are using a single for loop. For int I is equal to 0, I less than n, I plus plus, and we are assigning the value b of I is equal to a of I. Okay, so here this will depends upon the value of n. If we take for example n is equal to 5, so how many times our loop will execute? Our loop will execute 5 times, right? And if you take for example n is equal to 10, n is equal to 10, so it will execute 10 times. So if you take for example n is equal to 15, so how many times it will execute? 15 times. So it is depending upon the value of n. Right, so that's why this complexity is called as linear space complexity. Okay, n is equal to 5, n is equal to 10, n is equal to 15. It depends upon the value of n. So and next is a quadratic space complexity. So what is meant by quadratic space complexity? If you are using two for loops in the program, so that means for example a two-dimensional matrix. So here I'm giving an example int matrix n of n. So how many times it will execute? N into n square times. Okay, if I use one more for loop, right, that is n into n. So that means order of n cube. Order of n cube, right? So if you use two for loops in the program, it is 2 order of n square. If you're in 3 for loops, it is order of n cube. Like that, if you are using number of for loops in the program, so it will increases. So if you are using 4 for loops, order of n power 4. So it is called as a quadratic space complexity.